We'll start in a minute. Today we'll cover section 10.5 on the polar form of complex numbers. Okay, the first thing we'll talk about is plotting complex numbers in the complex plane. But first, we'll review what a complex number is. A complex number can be written in the form a plus b times I, where a and b are real numbers, and I is just the square root of -1, called the imaginary unit. So lowercase I is written probably because it's simpler to write I instead of always writing the square root of -1. The real part of a plus bi is the real number a, and the imaginary part of a plus bi is the real number b. Note, just as a side note, every real number is a complex number. A real number has an imaginary part that's equal to 0. Okay, a complex number can be plotted in the complex plane. In the complex plane, the horizontal axis is called, which is the real axis, represents the real part of a complex number. And the vertical axis, called the imaginary axis, represents the imaginary part. So if we put a vertical axis and a horizontal axis, the horizontal axis is the real axis. That is the axis on which the real numbers are. It's just the regular real number line. And the vertical axis is the imaginary axis. As you can see, it's not really imaginary. Imaginary is just a word that was picked by some mathematician to represent numbers that involve square roots of negative real numbers. Okay, so if we have a complex number a plus bi, where a is the real part, so suppose a is right here on the real axis, on the real number line, and suppose b is on the imaginary axis, then in the plane, this point is a plus bi. Okay, so we'll plot a few complex numbers in the complex plane. 3 plus 4i. So the real part is 3. The imaginary part is 4. So here is our 3 plus 4i. It will be useful to note that it's in the first quadrant. The four quadrants will come into play a little bit later. Plot this number 4 minus 2i. So the real part is 4. The imaginary part is negative 2. So this is the point 4 minus 2i. Okay, the real number negative 5. Well, I mentioned earlier that real numbers are complex numbers, but think of negative 5 as negative 5 plus 0 times I. So it's written in the form a plus bi. Okay, but the imaginary part is 0, so this is just a point on the real axis. I'll go ahead and write negative 5 plus 0 times I. And then negative 3i. This is equivalent to 0 minus 3i. So this number has a 0 real part. Sometimes when the real part is 0, the complex numbers are called purely imaginary. But to graph negative 3i, we just plot the point on the negative imaginary axis. So 0 minus 3i, or just negative 3i is okay. Okay, if we have a complex number z equals a plus bi, the absolute value of z, which is also called the modulus or the magnitude, is defined this way. We use the absolute value symbols to surround z. So the absolute value of z is the square root of a squared plus b squared. The modulus, or the absolute value of a complex number, is the distance from the point 0, 0 to the point AB in the complex plane. Okay, so we'll have some exercises where we find the absolute values. If z is equal to 3 minus 4i, then the modulus, or the absolute value of z, is the square root of the real part squared plus the imaginary part squared. So we're only using the real part and the imaginary part to find the modulus. We're not including I in that. And then we just do the arithmetic. So we get the square root of 9 plus 16, which is the square root of 25. And so the modulus is 5. That is the distance from the point 0, 0 to the ordered pair 3, negative 4 in the complex plane. Okay, for this one, same sort of thing, but just different numbers. If z is equal to negative 8 plus 2i, then the modulus of z is the number negative 8 squared plus 2 squared. And then do the arithmetic. Negative 8 squared is 64 plus 2 squared is plus 4. So we can simplify a little more. The square root of 68 The square root of 68 is the square root of 4 times 17. So the modulus is 2 times the square root of 17. Okay, one more. If z is equal to 12 plus 5i, then the modulus is the square root of 12 squared plus 5 squared, or the square root of 144 plus 25, which is the square root of 169. And so the modulus of z is 13. Okay, the next topic is write the polar form of a complex number. Okay, this says a complex number z equals a plus bi is in rectangular or Cartesian form because a and b are the coordinates of the point a, b in the complex plane. To write z equals a plus b times I in polar form, we let r be the modulus of z, which is the square root of a squared plus b squared, and we let theta be the angle in standard position whose terminal side passes through the ordered pair AB. Okay, so if we have a plus bi in the complex plane, then if we construct the line segment from 0, 0 to the point AB, then r is just the modulus of z, and this is the angle theta formed from the standard position. So in this case, theta is counterclockwise from the horizontal positive real axis. And what else? Well, as an ordered pair, this point is AB. The real part is A and the imaginary part is B. So tangent of theta is equal to B divided by A. I'm sure you remember, but if you construct this right triangle, then from the origin to this point on the real axis is A, and the vertical side is length B, so tangent of theta is B over A. If theta is in the first quadrant, then theta is just the inverse tangent of B over A. And you'll remember that if theta is in the second quadrant, then theta is not equal to inverse tangent of B over A, but we can use inverse tangent of B over A to find theta. In that case, it would be pi minus inverse tangent of B over A. Okay, so the polar form is z equals the modulus r times cosine of theta plus I times sine theta. Okay, this is the polar form. Okay, in this first couple of exercises, we'll convert the complex numbers from rectangular form to polar form. So let's note where this one is, this complex number. Where is it in the complex plane? So the real part is -2. The imaginary part is +2. So it's in the second quadrant. So we want to find the polar form. So we want to know what this angle is. And we also want to know what the modulus is. So r is just the modulus of z, which is the square root of the number -2 squared plus 2 squared. So we get this r is the square root of 8, which is 2 times the square root of 2. And theta is in the second quadrant, but we can start by saying, well, tangent of theta is equal to 2 divided by -2, or -1. Okay, so the inverse tangent of -1 is in the fourth quadrant. And we know that tangent of -pi/4 is equal to -1. But the theta that we want is -pi/4 plus pi. But we also know that tangent of 3pi/4 is -1 in the second quadrant. And it turns out that -pi/4 plus pi is this angle that we want, 3pi/4. Okay, so I wasted all my space. Where am I going to write the polar form? So I'll squeeze it in up here. The polar form for z is r 2 times the square root of 2, and then times the quantity cosine of 3pi/4 plus I times sine of 3pi/4. So I hope you can see that. Okay, let's try this one. Z equals 8 minus 15i. So this complex number is in the fourth quadrant. So 8 and say minus 15i. Well, if we want our angle to be between 0 and 2 pi, Then we move counterclockwise. This will be our angle theta. The modulus r, I should say r is equal to the modulus of z, which is equal to the square root of 8 squared plus negative 15 squared. And this is the square root of 64 plus 225. Or the square root of 289. And the square root of 289 is 17. Yeah. Okay, so that's what r is. And tangent of theta is equal to negative 15 over 8. And tangent of theta, well, we want theta to be between 0 and 2 pi. The inverse tangent of negative 15 over 8 is negative. So it would be this angle right here moving clockwise. So to get the theta that we want, we have to add 2 pi to this tangent of theta. Or I should say, theta will be equal to 2 pi plus the inverse tangent of negative 15 over 8. So just to reiterate, this angle right here, this is the inverse tangent of negative 15 over 8. So we're going to add 2 pi to it to make the angle theta be between 0 and 2 pi. Okay, so our polar form, z is equal to 17, that's the modulus, times the quantity cosine of that big angle, cosine of 2 pi plus inverse tangent of negative 15 over 8 plus I times sine of the same angle, 2 pi plus inverse tangent of negative 15 over 8. Okay, if that isn't clear enough, a little bit later I can write it out on paper that has more room on it. Okay, converting complex numbers from polar form to rectangular form. That might be a little bit easier, especially if the angles involved are either special angles or have reference angles that are special angles. So in this one, we just first evaluate cosine of 120 degrees. So cosine of 120 is negative 1/2. And then sine of 120, it's in the second quadrant, so that's square root of 3 over 2 times I. And then we can distribute multiplication by 4, and we get z equals negative 2 plus 2 times the square root of 3 times I. So this is the rectangular form, the a plus bi form. Okay, the next one, 6 times the cosine of 330 degrees plus I times the sine of 330 degrees. So 330 degrees is in the fourth quadrant. Cosine is positive in the fourth quadrant. Cosine of 330 degrees is the square root of 3 over 2. Sine of 330 degrees is negative 1/2. And then we do a little bit more arithmetic. 6 times the square root of 3 over 2 is 3 times the square root of 3. And 6 times negative 1/2 times I is negative 3i, but we'll write it as minus 3i. Okay, that's the rectangular form, the a plus bi form. And then this last one, z equals 12 times the quantity cosine of pi over 6 plus I times sine of pi over 6. So z is 12 times the quantity square root of 3 over 2 plus 1/2 times I. So z is 6 times the square root of 3 plus 6 times I. Okay, that wasn't too bad. Okay, we'll look at products of quotients of complex numbers in polar form. So I might need more space for this, so I'll write this on a piece of paper and we'll do the computations using more space. So Z1 is R1 times the quantity cosine of theta 1 plus I times sine of theta 1. And Z2 is R2 times cosine of theta sub 2 plus I times sine of theta sub 2. So the first thing we'll do is we'll show what happens when we multiply Z1 times Z2. Okay, so Z1 times Z2. Well, let's multiply R1 times R2 and bring that out front. So R1 times R2. And then we'll multiply the quantity cosine of theta sub 1 plus I times sine of theta sub 1 multiplied by the quantity cosine of theta sub 2 plus I times sine of theta sub 2. So these R1 and R2 are just real numbers, R1 times R2. And then we're going to multiply this quantity times that. So cosine of theta 1 times cosine of theta 2. Cosine of theta 1 times cosine of theta 2. And then plus cosine of theta 1 times I times sine of theta 2. So I'll write that as plus I times cosine theta 1 times sine theta 2. And then plus I times sine of theta 1 times cosine of theta 2. So plus I times sine of theta 1 times cosine of theta 2. And then we have plus I times I, which is I squared, times sine of theta 1 times sine of theta 2. Okay, remember, I squared is negative 1. I to the second power is negative 1. So this term right here is equivalent to subtracting sine of theta 1 times sine of theta 2. Okay, so in the next part, we'll rearrange the terms. We'll put the real parts together, which is cosine of theta 1 times cosine of theta 2. And then I'm replacing this with minus sine theta 1 times sine theta 2. So that's a real part. So minus sine of theta 1 sine of theta 2. And then the two middle terms each have a factor of I. So I'm going to factor I out of each of those products. So we get I times the quantity cosine of theta 1 times sine of theta 2 plus sine of theta 1 times cosine of theta 2. Okay, so we see some old formulas. That we can apply. Cosine theta 1 times cosine theta 2 minus sine theta 1 times sine theta 2, that's just cosine of theta 1 plus theta 2. And then plus I times remember this formula. These are kind of rearranged a little bit differently, but this is just sine of theta 1 plus theta 2. Okay, so I'll rewrite this on our lecture notes just to summarize. So Z1 times Z2 is R1 times R2 times the quantity cosine of theta 1 plus theta 2 plus I times sine of theta 1 plus theta 2. Okay, but now we'll do the second part, which is, okay, so given that Z1 is R1 times this quantity and Z2 is R2 times that quantity, this time we want to divide Z1 by Z2. So Z1 in the numerator is R1 times cosine theta 1 plus I times sine theta 1 divided by R2 times cosine theta 2 plus I times sine of theta 2. Okay, so what we do is we're going to multiply by 1 in the form cosine theta 2 minus I times sine theta 2 over itself, cosine theta 2 minus I times sine of theta 2. So what I'm doing is I'm taking the conjugate of this denominator, this factor in the denominator, and then multiplying both the numerator and denominator by that. So we'll do the multiplication. So up here we have R1, and then cosine of theta 1 times cosine of theta 2. And then minus I times cosine of theta 1 times sine of theta 2. And then plus I times sine of theta 1 times cosine of theta 2. And then minus I squared sine of theta 1 times sine of theta 2. So that's in the numerator. In the denominator, we have R2. This is going to work out a little more nicely because we're multiplying same terms. Cosine of theta 2 times cosine of theta 2 is cosine of theta 2 squared. And then I have minus I times cosine of theta 2 times sine of theta 2. And then I have plus I times sine of theta 2 times cosine of theta 2. And finally, I have minus I squared sine of theta 2 squared. Okay, in the numerator, we'll note that over here we have a minus I squared, which is like minus negative 1. So this becomes plus sine of theta 1 times sine of theta 2. So we'll put the real parts on the left, cosine of theta 1 times cosine of theta 2 plus sine of theta 1 times sine of theta 2. And then the I parts, well, we can write minus I times the quantity cosine theta 1 sine of theta 2. And we're factoring out a negative I, so this is minus minus sine of theta 1 cosine of theta 2. Okay, so that's the numerator. Then the denominator, R2. Notice the middle terms cancel each other out. One is negative, the other one is positive. We have another minus I squared, so that's plus 1. So all we have left in the denominator is R2 times cosine of theta 2 squared plus sine of theta 2 squared. So this is just 1. So we get R1 over R2. Since we're divided, this is just 1, we can ignore it. And cosine of theta 1 times cosine theta 2 plus sine theta 1 times sine theta 2. This is cosine of theta 1 minus theta 2. And then over here we have minus I times this is sine of theta 1 minus sine of theta 1 minus theta 2. Let's apply this formula to this example. Z1 is equal to 4 times cosine of 4 pi over 3 plus sine of 4 pi over 3. And Z2 is 2 times the quantity cosine of pi over 2 plus I times sine of pi over 2. So if we find Z1 times Z2, we can just use this formula. So the R1 times R2 is 4 times 2. And then cosine of the sum of the angles, 4 pi over 3 plus pi over 2. And then plus I times sine of 4 pi over 3 plus pi over 2. So we'll simplify a little bit more. 4 times 2 is 8. And then times the quantity cosine. So this will be 11 pi over 6. Yeah, I think that's right. And then plus I times sine of 11 pi over 6. And we can evaluate these. Cosine of 11 pi over 6. Well, 11 pi over 6 is in the fourth quadrant, so this is positive square root of 3 over 2. And sine is negative in the fourth quadrant. Sine of 11 pi over 6 is negative 1/2. So we can write this as 4 times the square root of 3 minus 1/2 I. Okay, let's move on to the next page. Okay, so this is similar to what we just did. This says if z is equal to r times the quantity cosine of theta plus I times sine of theta, and if n is a positive integer, then z to the n, if you raise the complex number to the nth power, then when removing parentheses, we get r to the n times the quantity cosine of n theta plus I times sine of n theta. So let's first show that z squared satisfies the formula. We can do this directly if we just multiply r times cosine theta plus I times sine theta, multiply it by itself. So we get to practice our formulas. So r times r is r squared. And then cosine of theta times cosine of theta is cosine of theta squared. And then plus I times cosine theta times sine theta. And then plus I times sine theta times cosine theta. And finally, I times sine theta times I times sine theta is plus I squared times sine of theta squared. And I squared is -1, so we get z squared equals r squared times, well, the real parts will be cosine of theta squared and then minus sine of theta squared and then plus I times cosine of theta sine of theta plus sine of theta times cosine theta. And then finally, cosine of theta squared minus sine of theta squared is cosine of 2 theta and cosine of theta times sine of theta plus sine of theta times cosine of theta is sine of 2 theta. So we can see that the formula works for n equals 2. And we won't do it, but we could use an inductive argument to show that it's true for all positive integers n. Okay, so on this one, we'll compute in brackets 5 times the quantity cosine of 75 degrees plus I times sine of 75 degrees to the 4th power. And then afterwards, we'll write it in rectangular form. So to do this, we just apply the formula. So this is 5 to the 4th times cosine of 4 times 75 degrees plus I times sine of 4 times 75 degrees. And let's see, 5 to the 4th is 625. So 625 times cosine of 4 times 75 is 300. Cosine of 300 plus I times sine of 300 degrees. And we know how to evaluate cosine of 300 degrees. 300 degrees is in the 4th quadrant. Cosine is positive. So cosine of 300 is positive 1/2. And sine of 300 is negative square root of 3 over 2. So our rectangular form, 625 over 2, and then minus 625 times the square root of 3 over 2 times I. Okay, we're about out of time. I'll just mention what you can do on this one. First, you can write -3 plus 3i in polar form. And this one isn't too hard to figure out. -3 plus 3i is in the 3rd quadrant, and the tangent of theta is -1. So the angle is 3 pi over 4, and the modulus is the square root of 18, which is 3 times the square root of 2 So cosine of 3 pi over 4 plus I times sine of 3 pi over 4. And then you just want to find z to the 6th using the formula that's given above. So it's not yet 1240, so we can write it out a little bit. It's 3 times the square root of 2 to the power 6 times cosine of 6 times 3 pi over 4 plus I times sine of 6 times 3 pi over 4. Okay, so now we're out of time. Tomorrow we'll cover the last 2 sections for the summer session, but that's all for today.